I may call Dr. Talat Zishan for the recitation of Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم والضحى والليل إذا سجى ما ودعك ربك وما كلا وللآخرة خير لكم من الأولى ولسوف يعطيك ربك فترضى ألم يجدك يتيما فآوى ووجدك ضائلا فهدى ووجدك عائلا فأغنى وأما اليتيم فلا تقهر وأما السائل فلا تنهر وأما بنعمة ربك فحدث صدق الله العظيم.
Jazakallah khair. Now with this, we start our first session with our worthy speaker, Professor Dr. Shahid Hussain, working as a professor at School of Material Sciences and Engineering, Jiangsu, China. He did his PhD from Chongqing, China, and also the postdocs degrees in 2015 and 2017. His field of interest are metal oxides, sulfides, MOF materials, supercapacitors, and LIS batteries. He has published more than 235 journal research articles with the H index 40 and 500 plus citations. Please, Dr. Hussain, start your talk with us.
Thank you so much. Bismillah ar-Rahman ar-Rahim. Can you hear me?
Yes, we can hear you.
Yes, just a moment, because here we have some, we have to use a VPN to go for the Zoom software, because mostly we use type of software. So thank you so much for inviting me to this webinar for material science in current era, because the current development in both in physics and chemistry and chemical engineering as well, they have elongated as a huge development in the field of science. So on with this emerging sciences, material science and engineering has also been coming up with many diverse application, and also new trends and diversities in the field of science, and also many development towards the humanity as well. Although there have been advantages and also beneficial to the humanity under this under the umbrella of these natural sciences and industrial engineering sciences as well. Of course, there have been also some risk factors that have been involved for these or maybe due to these sciences as well. So today I will talk about progress, recent progress. Specifically, I will focus on 2D heterostructure type of nanomaterials for gas sensor industry. So topic will be about atomically thin layer 2-dimensional heterostructure for sensing or gas sensor industry. So basically, I belong to Jiangsu University, School of Material Science and Engineering. I'm working here about more than 5 years, and my PhD, as you have been already introduced, about from also from China, and my postdoctorate. Then I joined here as associate professor, and based on these my profile, he was promoted here as a full professor. And now you have my group as well. This is my group and one of our dean also, and my students. I just put on a few pictures because my group is more than about 20 students now. So firstly, I will just give a brief intro about our school, because before going towards just like introduction about our school. The department is based on basically on the main 6 areas or main 6 disciplines. We are working for a School of Material Science and Engineering. The first one is metal materials and metallurgical engineering, then alloys and compound. Specifically, most of the aeronautical things, they are made up of alloys. And then material forming and technology, and the most advanced also polymer material, and then organic and inorganic metal material devices. Besides that, we also have 2 more institutes just in our department. This is all about our department: Green Energy Material, Organic Green Materials for Metallurgy Institute, or directly we also have New Energy Material Research Institute as well. So this is the basic structure of our department. We call here as a School of Material Science and Engineering. And here we do research on new materials, advanced materials, then high-tech equipment manufacturing is our target. We do also mine technologies, electrical vehicle technologies, EVM, like electrical vehicles, motors these days, and also work on marine equipment engineering as well. And also we also deal with the data adoption and other like simulation processes using the DFT and other simulation things as well. Our application, basically, they are focused on the medical apparatus and also intelligent grids and IoT, clouding computing as well, pressure, gas, variable, and sonar, and DIR type of these all kind of sensors as well. And also polymer based material sensors, and all these things in my group, we work on 3 kind of material basically. Most material, you are well aware of those, that is metal oxide, semiconducting materials, then the upsurging or upcoming, or now these days are in the market material, they are more metal organic framework, although they just serve as a template. And then finally, the most advanced material these days, they have been magazine. So magazine, I will introduce about also magazine here today, because these are mostly used 2-dimensional nanostructure material. As you know, due to just as I mentioned before, due to the emerging scientific developments, and also the key requirement from energy and also other processes, environment has been polluted at a huge scale. So we have to control it at somehow, some nanoscale, or some maybe at macro scale, not on the nanoscale, or maybe if we can control on the nanoscale, then we can go on the basically on very macro scales. So from homes to industry to environment and the workplaces as well. So although to control all these factors, there have been many other, but the most important thing is to detect the exact concentration or the quantity of those pollutant or hazardous material in the environment. For that, we develop a kind of device that we call it sensing device, or we call it gas sensors. So here I don't introduce about, because this has been, so among those gases, just I said about some of the gases are hydrogen sulfide gas, carbon oxide, carbon monoxide, carbon dioxide, nitrogen dioxide, or simple nitrogen gas, or sulfur dioxide, or sulfur gases, and then also VOCs. Of course, these all or other gases, they have adverse effect on human health as well. So for those, we use a kind of device, we call it gas sensors, or gas detector, maybe a word some people use, but those, when specifically we talk it in a technical term, for us detector sensors, they are different. And then they're in the intermediate also, that is called actuator. So a word directly defined for this all system is called sensor, actuators, and detectors. So here I will focus on the sensors only. The sensor, they basically only produce the interaction with the target gas and also the electrical signal of, just like simply define it, if I say it is taking the electrical signal into a physical input, a physical output. We can see, like, if you cannot see, if you cannot hear, you cannot smell, or you cannot be detected. So the focus is on few things, like we can prepare electrical or electrical skin, or maybe electrical hearing, just like I'm using here. And of course the microphone we are using, this is a microphone. If someone has a other problem, like if you remember the guy who is Stephen Hawking, the black hole concept guy, he has many problems, so he was using the 5 kind of sensor at the same time with his a single chair. And one of them is electronic nose. So electronic nose, we call it as a gas sensor. Is there any problem?
No, sir.
Okay, so I can go on. So some of the catalytic gas sensors, they have different type. Of course, just I said, as there are different type of gas sensor, there have been diverse industry and the requirement. For example, the detection of alcohols, they are different. The detection of food poisoning, they are different kind of sensors. They can also be smelled as well. And also, like if we need detection of gases in case of radiations. So they have been gas sensors are based on 5 different reactions. One is catalytic bead reaction, infrared sensor or infrared reaction, then solid state of sensor, and then electrochemical and photoionic type of system. Here I will focus on the chemical type of sensor as well. But the one is type of catalytic bead type. It has 2 basically, electrochemical and chemical type of sensors. So what they do, they are prepared for the amplifier. Then we use a sensor array, set of sensors. I will show it later. And then we test with the system that is signal processing. And then we get a pattern of predefined recognition system that we call it pattern recognition system. So the key parameter for the sensor system, there are 4 kind of system. We call it 4S system. One of them is the response. The other one is selectivity, then stability, and the temperature as well. A response defines the time or the reaction of the sensor with the adsorbed gas molecules on the surface of the sensor with the preset nanomaterial, like it may be MOS, or it may be MOF, or it may be magazine, any kind of material we are using. So sometimes it gives after the interaction, it gives us some resistance that we call it response. But also we have another thing is that is recovery. I didn't mention here, recovery means the time in which it will come back to its original state. Then the selectivity. Before selectivity, I say about the stability and temperature. So stability, we will talk about the time in which, how long it can retain, or how many days or how many years it can be retained at the same time. The similar response for the whole system. But although, because due to the environmental factor, it has been very easily, it can be polluted. So the temperature is a temperature, we call it working temperature. It has many for different materials and for different gases, the working temperature is different. And then finally the selectivity, because in the environment actually there are many gases. So we also use single gas detection, we also use multiple gas detection, and also the same time we use gas mixture system and then detect the possible gases that can be detected. And one of the gas is always give a maximum response. That may be a reducing gas or maybe oxidizing gas. One of them it can. So we call it the selectivity. So all these parameters, I will later use a word key term that will be optimal condition. So all these factors are when we define, we say this is optimal condition for some specific material for the specific sensor. So gone height of optimal working temperature, of course it is not good. We need a low temperature detection system. Then poor selectivity, of course this is also a problem among the different materials. Specifically, these are the problem with the metal oxide type of systems. And then the response is lower than poor recovery, especially at the room temperature systems. So you can see at the bottom we have one of the figure. This is our company or industrial commercial type of sensor we are already working on. And there are 4 basically steps: synthesis, processing, then structuring and property of that material. I will show the bottom figure in 3 different sets. So three type of materials they have been used for generalize. If I have generalized here because my topic was on the diversity and or trends in the nanostructure for the specifically these gas sensors. They can be 0 dimension, 1 dimension, 2 dimension, 3 dimension. So there may be question which one is the best. Of course, all of them are the best one. They It depends upon the application where we want to utilize them, and then there may be another question where we what is the main structure that can be utilized for which kind of specific direction. So this is not hit and dry. So it depends. If we need a low temperature, high response, then we see 3 dimensional. If we need a strong response for higher stability, then we use 2 dimensional structure. And if we want to use longer response with short recovery, that we use 0 dimensional type of structure. So these are all intermingled or intermixed structures we use at the same time for different applications. This all depends where we want to employ our prepared or fabricated gas sensors. So this one I have already described, so there is no need to go on for this one. Gas sensor, they can be used in a different field for the biology, for the photo, for the electro, and we will discuss about the preparation and application and working mechanism as well. So first of all, I will give a brief idea about the different three testing system. The first one is the older one, but this kind of testing system, it uses a voltage based systems. So you can see there on the right side, you can see there is a box. This we call it chamber. Inside the chamber, I have a larger image. If my cursor is moving, I can show you the and it is working. So here are fans. One is for exhaust, one is for evaporation. So and there is an array of sensor. You can see in the figure here. Inside there are about
5. Sir, we cannot hear you. I think Professor Shahid, the internet connection is creating some problem, so we will wait for a while. We may shift our So we may shift to our next speaker, Dr. Shabnam Jabeen, currently serving as an Associate Research Professor in Physics Department, University of Maryland, USA. She did her PhD from Kansas University, USA. She has expertise in particle physics, accelerator or detector particle identification, statistics, and MC simulation. So we may proceed to Dr. Shabnam Jabeen to present her work with us.
Let me just share my screen.
Yes, please.
Can you see this?
Yes, it's going. Yes, we can see. Yes, Dr. Shabnam, we can see your screen. And
All right, very good. So, well, let me first say thank you for the nice introduction, and thank you for inviting me. I want to say special thanks to Professor Dr. Sufia Iftihar for inviting me. I am not really sure why I am here because I am not a material scientist. So I'll just share my new passion, which I'm hoping that all of you will find very interesting. And I will try to make connections to material science as I go. So I am going to talk about quantum computing, and I will share with you the latest in the field. In that sense, as I'm sure many of you know, it's an extremely new and very rapidly developing field. I will make material science connections where I can, and I'm hoping that some of the new people will pick up. So I am not sure how many here are students, but my talk particularly is geared towards the new incoming young blood and people who are looking at the horizons of science and new technologies. So why quantum computing? It's not long ago, just a few decades ago, it turns out that there are technology, algorithms and technology that can exist that can make it very easy to hack our current very secure encryptions. For example, the RSA, as you know, it's based on prime factors. And to find those prime factors that make up a key is not easy. It is very hard computational problem. Classical computers cannot do it very quickly, which ensures the privacy of our data and any other place where we need encryption. But if we have quantum computers, which we are working on, these algorithms actually can do it exponentially faster, which means that once you have quantum computers, nothing is safe. That's an easy thing to infer from here. And this is the reason that everybody is suddenly, after this, suddenly jumping. So before I talk more about quantum computers, I do want to talk about quantum because all of us are physicists. And coming from that side, there are special qualities in quantum that I want to just highlight in a little bit. So I will just start from the beginning. And as I said, my talk is geared towards more young people and students. So I'm just taking the time to go through these simple details. So as anyone knows, we have only 4 fundamental forces, and all of those, everything else that we see is an artifact of these forces, whichever, whatever it is in biology or chemistry or any place else. And these forces and the phenomenon concerning them are explained by 2 basic theories. One is the general relativity, which explains essentially everything concerning the big galaxies and clusters of galaxies. And then standard model, which is based on quantum mechanics, is describing all the phenomena concerning atomic and nuclear forces. And by the end of 19th century, early 20th century, we were already essentially finished setting up the physics of the world around us, the visible world around us. And the picture was quite nice. We could explain, we could solve almost every problem that physical world was throwing at us. And to the point that people at that time started saying that, well, everything is, we already know how to solve everything. The only thing we need to do is to keep repeating our experiments and make them more and more precise. And it wasn't such a strange statement, except there were only a few things. For example, black body radiation wasn't understood, and people weren't that worried about it. But it turns out that in order to understand those things, we actually ended up having 2 revolutions in physics. And those revolutions, in fact, they did not change the way we look at physics, but they also changed the way we look at the universe around us in terms of space and time, or philosophical questions like free will. And those, as you know, those revolutions, one was the general relativity in 1905, and the other one was quantum mechanics, which started with the paper by Planck in 1895. And as you know, Einstein's Nobel Prize paper was actually the first one which gave us the idea of the actual quanta of energy. And this is a funny thing, because Einstein got Nobel Prize for this paper, but then the rest of his life, he actually tried to fight the ideas of quantum that he actually fathered. And so quantum mechanics today that we have, there are many interpretations. And this is again a strange thing about quantum mechanics, that the theory that standard models such an extremely successful theory based on quantum mechanics, but the 4 ideas, we still are struggling to interpret them, what exactly they mean. For example, the most common and famous one is Copenhagen interpretation. But that interpretation tells us that there is probability involved. There are superpositions of states, like the Schrodinger's cat, which can be alive or dead at the same time. And there is something called entanglement. All of these things have no classical counterparts. And this is what makes quantum mechanics so special. It's kind of strange, fascinating, but somehow it works. And we are still struggling to understand these things. But again, as I said, and as you know, this thing works extremely beautifully. And just to remind us, Einstein and Bohr, for example, had a long fight between themselves. And Einstein's famous quote is, God does not play dice, is in fact coming through this whole fight. His dismay over this uncertainty and indeterminism that comes out of quantum mechanics. And in fact, when he was writing this EPR paper, one of the things that came out in the newspaper, the words that were used were system of delusion for quantum mechanics and the concepts. But now we see this year, a Nobel Prize is given to Alain Aspect. And I'm sure you all know Alain Aspect did the experiment in the 80s, which proved the experiment that on Bell's theorem, which essentially proved experimentally that quantum mechanics is the way of the universe. Bell's theorem already proved that theoretically and almost put the Bohr and Einstein feud to rest, but Aspect actually proved it. And if you look at the Nobel Prize Committee's wording, they say that this is for establishing the violation of Bell inequalities and pioneering quantum information science. So again, here we see that this is a nod to this revolution, quantum computing, that is really, really flourishing at this time. And as I said, quantum mechanics, we do not understand it even today. And as you know, I think there is nobody famous in physics who actually feels comfortable about it, including Feynman, who devised quantum electrodynamics, Gell-Mann, who started QCD, and Bohr himself. But that does not stop us from using it, and we have been successfully using it as in terms of, for example, standard model. I mean, everything that is based on quantum mechanics works very nicely. Quantum computing in itself essentially started with Feynman, where his famous quote is that, damn it, if you want to make a simulation of nature, since nature is quantum mechanical, you have to have a quantum mechanical computer. And since then, Feynman gave ideas about quantum computers as well. And since then, today we are at a point that quantum computers, everyone who wants to bet on a future technology is actually putting money on quantum computing. So it's governmental level as well as the private sectors, where we are now talking about billions, and soon it's going to go to trillions of dollars that are being thrown at this industry, both experimental and theoretical work. And you will see we are quite far in that sense. So before I get to the actual quantum computers, let me just give you an idea of what is the difference between classical and quantum computers. So in classical computers, we say a bit, or the data is used in terms of bytes. So a bit is nothing, it's just a 0 and 1 state. So current on is 1 and current off is 0, that's all. And 8 bits make 1 byte, and 8 bits means you can have zeros or ones or zeros or ones, and you can put information in those zeros and ones, and that's how you can manipulate it through the value of current. You can flip a bit and you can write something in computer's memory. And for example, if you have 8 bits, that means you can have 1, 1, 1, 0, 0, 0, these 8 numbers you can have there. And in those 8 numbers, you can have 256 variations of those numbers. But the state at one single time is just 1. You can write one kind of 100100 number. Only one state is possible in one given time. On the other hand, if you look at a qubit, it's not just 0 and 1. It's a quantum mechanical 2-level system. And we know that quantum mechanical systems can exist in a superposition. So the superposition means that any state, it's a superposition of or simultaneous 0 and 1. So your 1 bit is not just 0 or 1, it can be 0, 1. And when you have multiple bits, you can have this 2 to the power n dimensionality to these states. So what does that mean? It means, for example, if you have 80 bits, you still have one state that you can store in one time, or one state that you can look at one time. But in quantum computers, if you have 80 qubits, that means you have 2 to the power 80 states. And if you write down that number in its actual form, the number is actually bigger than the number of atoms that are in the visible universe. We can estimate that. It's such a huge place where you can store such a huge number of information, and the number of states that's available to us in terms of qubits is astronomically better than anything else we have seen so far in terms of computing power. And that is what makes quantum computers so precious. Now, I want to give you some idea how actually quantum computer works. And when we say that quantum computers are very, very fast, what does that actually mean? And here it's a small example that if you have 2 points and you want to go to one point from point A to point B, and let's say there are 8 different paths to get there, and you want to know what the shortest path is, the worst case scenario is that if you do not have any other information, you will actually have to walk every single path, one after the other, and then figure out which one is the shortest path. And that means that you have to have n operations done before you can do this, you can make this decision. On the other hand, if you have a quantum computer, you do not have to do this one by one. This whole thing is one state. You can look at it and you can readily pick the one that is the shortest. And here is a small example. And the reason I have this slide is just to show you that even though we say quantum mechanics is we do not understand, or we interpret, there are different interpretations, or we are still debating what it means. There is probability, and there is indeterminism, and there is entanglement. But in the end, it is all mathematics. So we know the rules the universe is following. They all come down to some sets of mathematics. For example, in this case, we are talking about Hilbert space. And those mathematics, in this case especially, it's just linear algebra and matrix multiplication. And once we do that, everything falls into place very, very nicely. And when we go and we actually measure those things in quantum computers, we actually get what we can prove from this mathematics. So even if we do not understand quantum mechanics, we know that universe is speaking in terms of this mathematics, and that mathematics works extremely beautifully. So in this case, if you have, let's say, there is a set, let's say 8 names. You are on Google, and Google comprises of, someone trying to talk to me? Okay, sorry. All right. So, so if you have a set of 8 names and you want to search, and this is just an example, we can search on Google for billions of things, and we can think of it as a small example of that. So out of 8 names, you want to search for one name. This specific Grover's algorithm, which is essentially mathematics, it will work in a way that it will create, we have this state of 3 qubits, which means we now have a state with 8 elements. All of those 8 names are encoded in those states, and your algorithm actually can go in, and if you can see my cursor, it can look at all of those 8 states at the same time rather than going through them one by one like a path. And it can look at the one it is searching for, and it can flip it. So the amplitude is now negative, and all we have to do is now amplify that amplitude. So rather than doing n times or n operations, you just did one operation to flip and the other operation to amplify. And that's how you get the exponentially faster algorithm, because in quantum mechanics, you don't have to search one by one. Everything is right in front of you in terms of those states, because quantum mechanical system can hold that many states at one time. And this is where superposition and entanglement comes into play. And this is what will make the thing that I said in the beginning, that cracking the code or breaking the encryption, like finding factors, prime factors for encryption keys, that will become much, much faster, much, much easier. So in terms of development, in terms of physical development, and the one that you might be more interested in terms of material science, this is an area where a lot of progress has already been made and people are still working on. The two that we are using are superconducting based quantum computers and trapped ion. And these are the ones that I'm going to talk a little bit about. I don't know how much time I have now. Is anyone keeping track? I don't remember when I started.
Madam, you have 10 minutes now.
All right. Okay, thank you. All right. So ion trapped qubits. So the way it works is the way the name is. You take an ion and you have one single electron in the valence shell. And once you have this one electron, it can, you can manipulate the spin of this electron in a way that it can be flipped. And since it is an electron spin, you can flip it in a way that you can flip it all the way up or down, or it can be in a mixture state. And this is what makes a qubit, where you can have a 0 state, a 1 state, up or down spin, or anything in between, which is combination of the two or the superposition of the two. And this makes a qubit with one ion. And the beauty of this system is that it is natural, and the coherence time, which is extremely important parameter for quantum computers, is very large. So that makes it very nice. So starting from the upper left corner, this is one atom. This is literally a picture of one atom trapped between these electrodes. And here you can see the chip on which this ion is trapped. And we are talking about a centimeter length. Here we are talking about, this is a blown up version, 4 qubits. And these qubits are like microns apart. This tiny chip is housed in this vacuum chamber, and then the whole thing is manipulated through these lasers and is read out through these photo readers. So this is how an ion trapped quantum computer or processor essentially is made. This is the one we have at UMD. Again, this is the same kind of chip. Here is the housing chamber. And here you can see a whole jungle of these lasers. And this is where a lot of material science comes into play, because making sure that all of this system works and the connectivity and the material, everything fits together and the noise is reduced in operations is going to be the key in order to get a commercial computer, which we don't have at this point. The other computer that is very popular, and people like Google and IBM, they have a lot of them. They are working on these constantly. And these, you can see that they are essentially superconducting. They are called superconducting. So that means that they require a superconducting, like a freezer, where you can have temperatures up to millikelvins, where you can house your chips. And the way that works is that this is essentially a superconducting foil, 2 wafers of superconducting material, and then you have a capacitor of superconducting material. You essentially are making an LC circuit. And once you have that LC circuit and it has a resonance, you can manipulate that resonance into levels. And once you have those levels, you can use it as a quantum entity with quantum levels.
So
is there a question?
No, ma'am, you please continue.
All right. So here we have, this is one of the latest things. So we have here 80 qubit ion trapped chip. You can see the chip, and this is a blown up version of, this is the actual ions trapped. There are 80 ions, and the distance between every single ion is like 5 microns. And you can see the precision of this thing, and that it can hold 80 qubits or 80 ions in this state. And this whole thing is like 1 centimeter. So it's an essentially very, very tiny thing, but the precision is extremely nice, and the coherence time is extremely large. So the technology has already developed quite a bit. Last year, IBM Quantum, they unveiled their 127 qubit quantum processor. So they are also getting very, very close to having sort of a commercial thing out. All right, so this brings me to the conclusion. I just wanted to share with you that the quantum computing, this is the new thing. Almost everywhere it is a new thing, and at UMD it is a big, it is turning into a big thing. We are going to be using this for LHC data analysis, hopefully very soon. it's here to stay, hopefully, and scalability at this point is very important. And this is where you guys will come in, because having the material that work with the precision and without defects so that we don't have noise, that is going to be the key in scalability here. And yeah, I mean, and material science from the other side, once we have the quantum computers, you guys will also benefit because you can simulate. It's very hard to, what I understand, is very hard to simulate new materials, but the quantum computers are going to make it extremely easy. And so any industry that benefits from those kind of materials will actually benefit from these computers. All right, this is all that I had to talk about. Thank you.
Thank you, ma'am. Very beautifully explained the very interesting topic, though it's very far away, but you explained it very beautifully, the quantum computing. The room is open for questions. Okay, thank you, ma'am. If no question, then we can move to our first speaker again and apologize for the signal issues and everything. Professor Shahid, you may continue.
Yes, please let me open the share.
Dr. Shabnam, you have to stop the sharing, please.
Let me do that.
Yeah.
Okay, thank you so much. And sorry for inconveniences that happened due to the internet problem here. Because I was, yeah, thank you. Can you see my screen now?
Yes, we can see your screen.
So we were talking about the testing system. First, I add one thing because just now I thank for the Dr. Shabnam. She was talking on the computing. Also, we also use such kind of system. We called it as a server here, and use a DFT simulation system that is based on the WASP software. And the similar thing is also done here on the one I showed before, NDIR type of sensor systems. So we also use a system as well. So going on, I was talking about the first type of sensor system that is based on chip-based sensor system. So three of the sensor system will be chip-based sensor system. Here we use an array of sensor that has been shown on the right side on the bottom in the chamber, and the chamber has been enlarged and zoomed. On the left hand side, you can see there have been temperature sensor that just for detection of for the setting of the temperature, then evaporator, and for the low and high voltage setting, and then the fan switches as well. And the system, how to integrate or how to fabricate the sensor is shown on the bottom. You can see on the right side as well. Specifically, see in figure C first. This is a pedestal sensor pedestal we use. There are 6 sockets on it, and we pass. First, we paste aluminum electrode on it, and then we pass a nickel chromium heater inside the electrode and engraved on the surface of the sensor pedestal as shown in figure D. And the circuit is shown here as also on the just beside the figure D. A single circuit totally engraved and compact made is shown in the highlighted one. And next one is about a type of CGTP system. Now we are using these 3 type of system here as well. This type of system can detect, can use one microprobe system. They have been used on the surface of the sensor, but although this system is more efficient and are a very small chip is used, maybe 100 of chips can be imprinted on one nail. So this is very small, like a kind of nano sensor as well. So as you know, there have been many small kind of devices or integrated circuits pasted on or put on the microboard or the chipboard of the computer. So this is the one how it comes from the backward technology. But because recently we are working on developing a sensor for a mobile company, they want to directly embed their sensor that can detect the gas directly rather than taking data from online system. Like some companies they take data from the Google, some companies they take from the data iOS and other sources, so then they update into the system. So now it has been already developed so that the direct detection can be done on the mobile as well. So this is one of the system I have shown here. You can see in figure D there have been 4 sensor arrays. Of course, they are of very small size. I have put the micro pictures of there here. So this is the measuring system is shown here. So these 3 systems we have been using here since maybe more than 5 or 6 years in my lab, and my students are working on it. So for developing of the gas sensor system. So this is the detection of particle molecule, how it is detected. It is totally about the physics, is clear physics from the absorption to scattering, and then from the anti-Stokes or the Stokes-Raman scattering. So there have been 2 types of course, all of you know and more aware than me, because you are of course elder than me and know about these kind of rotation. So, but actually these kind of rotation, they give some excitation or de-excitation of energy. So from where we detect our exact molecule system, how much energy is liberated or how much energy is absorbed. So we can detect each electron or single molecule very easily, but that's all based on the spectroscopy or those kind of machine that we are using here. The basic theme is also taken from the physics, also from the quantum mechanics as well. And 2 kind of gases, basically for oxidizing gases, they have tendency to accept electrons, among them oxygen, nitrogen oxide gas, and then carbon dioxide gas. And they accept electron from the surface of material and absorb more quickly with the sensor surface under the normal temperature condition, like it is less than 50 or under the 100 Celsius centigrade. This, of course, the absorption is very important. That can be increased by increasing the temperature and the size of the particle, or also with the doping. Mostly, just for here, I just say in this kind of devices, the important thing is to change resistance and keep the resistance as low as possible. And for under the 100 Celsius centigrade, there is a release of 1 electron, or it can accept 1 electron in case of oxidizing gases. And also above 200 or more than 200, it can accept 2 or electron or more than 2 electron. So it all is about the interaction of gas molecules and also the material that is coated on the surface of the sensor. If the gas is redox or the reaction is redox, so the process is totally converse type of process system. So I will talk about the 2D magazine material here. Magazine material, they have different sets. They come from basically aluminum, silicon, phosphorus, gallium, germanium, arsenic, and so on. And then the max material, A come for the SCTI, CR, and so on. So we call it max material, and their intermediate material is either fluorine or oxygen, carbon, or nitrogen. So titanium is the basic material as well that has been used in the magazine kind of material. For the heterostructure, if we want to develop a heterostructure among those material, I have just put one table to show here which kind of material they can be used for what kind of gases, and their selectivity, their sensitivity, their response, and how much concentration we can detect at what temperature. So you can see, for example, SN, MOS2, and so on, WS2, MOSE, and MOTE. All these material, they show maximum response at room temperature on the third, fourth column. And also for if we go down for graphene, graphene-related material like graphene and molybdenum disulfide, and graphene like aluminium nanoparticles at composite made with all the other up materials. So they also show response, but the temperature increases very, like it can go up to 150. So this temperature is mostly considered as high temperature, but for some application, temperature can go up to 400 to 500. Like for example, if we need to go beyond the space, and maybe some places it is under freeze, more less than freezing, like many minus Fahrenheit, or maybe some places the temperature is much higher. So it all depends where we want to utilize these kind of materials. So the maximum material they have been used for specifically for two-dimensional material have been shown here. The maximum response you can see is 300 response, that is for MOTE. Although this response is not that much higher, because one of my students recently, he got a response that is more than 6,000, and that is at room temperature also. This is ideal, but I haven't shown here. I will show maybe in some future time. I will show because that have not been published yet. So maybe I cannot put it that here. So these two-dimensional materials, they have intercalation. They have ion species. They have ionic or inorganic molecules type of system. They have been used in optical, magnetic, thermal, catalytic, energy storage, transparent, and so on, many application as well. So what's the basic theme or basic idea of using those such kind of material is their work function. This is most important, because as a physician, you also know that when we use some material, or when we are talking about, we always talk about the band structure system. We talk about this is formation band, this is like forbidden gap, this is valence band and conduction band, and so on. So these energy bands, like in our masters, maybe we have studied about the perturbation theory as well, like and also the wave function as well. So those all are taken from where they have been. Those ideas come basically from the heterostructure, or kind of those places where there is experimental based. If we talk about the band alignment of the metal semiconducting heterostructure, because what we read is not all about the metal materials, not about the metal oxide material, not all about the insulator material. The story is different for different materials, because mostly it has been discussed for hydrogen or sodium type of material. Those have a single valence type of atoms. The alignment of band structure or the band of the metal semiconductor heterostructure should satisfy the Schottky-Mott rule, in which the ohmic contact is formed. Mostly the ohmic contact is formed at the interface, that is according to the work function. And work function means work function for the material and also for the semiconductor. It depends on the type of semiconducting material as well. And then if we superficially, we talk when work function of the material is greater than the work function of the semiconducting system, that means there will be free electron near the interface, and they will be transferred to the side of semiconductor, and they will form a ohmic contact between the metal and a type of semiconductor. So semiconductor, you know, there are two types, N type and P type. So first, this ohmic type of contact, the resistance contact will be for when the work function of material is greater than the work function of Schottky one, that will be for N type. And if it is for the P type semiconductor, it will form another kind of contact, and the electron transfer will be between the semiconductor and the metal. They will continue until the Fermi level reaches. So Fermi level means it will go to the about 0 electron volt of energy, and there will be thermal equilibrium for those, and there will be no further conduction of those. So we will say that most of the material, they become like near about the insulator type of systems. And interface, I already talked about this. Interface has been shown. This band alignment, they chart transfer behavior in two-dimensional heterostructure material, semiconductor type of SSC, semiconductor material, and semiconductor insulate heterostructure material as well. So this all story I have talked about. You can see if phi m is less than or greater than phi s, it will be ohmic contact between metal and semiconductor. It will be N type semiconductor. If it is Schottky contact between metal and then it will be P type of semiconductor. So this schematic is also shown energy band diagram of molybdenum sulfide for p-n heterojunction based sensor that is under developed under the UV irradiation, because we can also illuminate or excite our surface electron using different lights like UV lights. We can also use different other lights to accelerate or excite those surface electron if they have not been accelerated or they do not show any resistance or any conduction through the testing system. So we use a force, a pressure to increase their kinetic energy as well. So this is the first one we have recently, like last year, maybe we have published in Applied Surface Sciences, that was enhanced as NO2 gas sensing performance of two-dimensional magazine, this Ti3C2 and titanium oxide composite by in situ formation of Schottky barrier. These are typical figure, for example, XRD, XPS, and other also illuminated like large as in convoluted type of XS figures. So you can see if some of you have material background, so maybe they can know easily these are XRD peaks have been well aligned with the what we have prepared as well. So I just go to the material formation. This is a scanning electron microscope, transmission electron microscope, images at different different sample prepared at different temperature. For example, you can see in figure A, this is simple max material, a simple magazine material, but then we dope with the titanium oxide. You can see in figure B, C, D, E, and F, they have been embedded very efficiently, very prominently, and uniform as well. And then they produce a heterojunction between Ti3C and TiO2. And in figure A1 to A2, A3, B1, B2, and B3, these have been like TEM or transmission electron microscope and higher resolution TM figures. And also SAED is shown in A4 and B4 as well. They show very relevancy with the our as prepared product that have been prepared on different temperature from room temperature to 220. This is the synthesis temperature, but we will next go up to the conduction band. We are also simulated the conduction band, also got the conduction energy band also simulated, and as well also we got experimental band gap diagram from both the set of equations. So also we did the gas sensing. This is the gas sensing curves for those as prepared material. You can see 180 or about 220. They show the maximum response for the NO2 gas, and we have tested like 4 gases: nitrogen dioxide, sulfur dioxide, NH3, and carbon monoxide. So similarly, we see maximum response was gained at 180 centigrade for nitrogen gas, and you can see if the air is purged, air is input for the first time, then the resistance goes up, then and gradually decreases as well. So we can see there is a time of recovery and time of response in figure A down on the bottom. The response time and the recovery time are low. They are very large, 300 second and 275 second. As I said in initial my two slides, because all parameters cannot be satisfied at the same time. So we try to control some parameters and then get specific output for specific sample. And in figure B, you can see it has been decreased to 150 second to 72 second. Of course, this recovery time is very good, not that bad, although the recent sample we have achieved the recovery time is about 10 seconds. So that is very sharp recovery time for that one. And also we tested our sample for the different humidity, because these gas sensors, they have been affected badly with the humidity effect from because they absorb oxygen on the surface of the molecule on the gas sensor and during the experiment. But after, when we fabricate the device, of course the environmental factor, they affect very intensively on the whole. And this is a simulation we have done on both. We have compared also the simulation results and also the experimental results. You can see both in figure E and F. They show a maximum response even for the simulated one, and also of course experimental, because that has been experimentally proved, and it gives a very good absorption energy, and also ultimately high response for nitrogen dioxide gas. And this already, because this is a typical curves just for the like supporting information or supporting data for different concentration have been tested for different temperature, different parameters, and linear response has been seen. Also, it shows a maximum linear response of 0.9, and that is more than ideal. So because it is very important to find detection limit as well. So here in this case, our detection limit was about 3 ppb for nitrogen dioxide gas. And for the next is for SNO2. मैं presentation करूँ 10 मिनट बाद आइएगा. After 10 minutes, Jesse, I'm online. And the other one is on the SNO2 with the magazine material. So this material for room temperature sensing, and the composition is with the tin oxide and titanium carbide composite, controlling the facet. We try to control facet. You can see in figure on the right side, maxine material is on the as a template, and then there have been polyhedral type of shape that have been embedded, or they have been floated on the outside of the max material. So typical figure also have been shown here for the Schottky barrier, and also for TEM and HRTM as well, and for the simulation one, that one for quantum effect as well. And you can see here figures, it is detailed structure for different samples with different construction. They show ultimate uniform nano structure for their synthesis process at the initial stage. And at the bottom also XRD figure has been shown as well. And secondly, also again XPS typical XRD figure with the different facets like 2 to 1 and other faces, because we focused on 110 and also 2 to 1 face, that because it is multifaceted. So we had a try to use double face of a single nanomaterial to get the multiple exposure of the gas molecule interaction with the fabricated material. So maybe it was thought that it could get a better response than the previous one. So it happened as well. It has given a better response than the previous one. You can see in figure A and also in figure F, it shows again maximum response for nitrogen dioxide gas, and the response was 1.6. This, of course, the result looks very small, but this is the percentage response. That means the response was about 160, and this response is also very ideal. Different concentration and different curves have been shown in figure. On the left hand is the figure A, that is also for humidity, but this sample was affected by humidity due to the usage of SNO2, because SNO2, zinc oxide, tin oxide, tungsten oxide, and other these single metal oxide, they are easily affected by the environmental factors. When the temperature is higher or lower, they easily decrease their response with the gradual increase of humidity. And Schottky barrier is of course is shown here. They show conduction of near the semiconducting type of material 2.41, and also afterwards, after the contact, they also show a very ideal type of conduction for the whole contact of the system. So just these are the publication, maybe no need to show. I'm working also for, this is the oldest one, because I'm working it in general as an editor almost for all kind of journals elsewhere, Hindawi, Springer, and so on. If you have any condition, any help needed, I can help for those things as well. And thank you for all. If you have any question, you are welcome to ask, please.
Thank you, Sir Shahid, Professor Shahid. So nice of you for such a interesting work, for presenting such an interesting work to us. Any questions from audience? Okay, if no question, then we will move to our next speaker. He's with us, Professor Dr. Muhammad Yasin from the Department of Physics, University of Agriculture, Faisalabad. He did his PhD in nanofluids and thin films from the University of Technology, Petronas, UTP, Malaysia, and MPhil degree in plasma processing from Quaid-e-Azam University, Islamabad. And he have also worked as postdoc fellow with the Director of Hybrid Energy System Research at UTP. He has published more than 450 publications, 200 journal publications with an impact factor of 450, and also involved in publishing the books and book chapter almost 24. He has been a member of supervisory committee of 105 AMPHIL students and 12 PhD students. He has presented his research work in more than 55 national, and international scientific events. Please, Dr. Yasin, share your work with us.
Yeah, thank you very much. Can you hear me, please?
Yes, we can hear you, and we can see your screen also.
Thank you very much for a nice introduction, and let me thank you and all the organizing team for organizing this wonderful event. I'm Dr. Muhammad Yasin Naz from Department of Physics, University of Agriculture, Faisalabad. And today I'm going to present on the waste management, especially the plastic waste into valuable production. For example, the production of the nanomaterials, and in nanomaterials, my focus is on carbon nanotubes. So the layout of the okay, the layout includes what are the good and the bad and the ugly things about the plastic waste in the Pakistan, and what are the mechanism of microwave assisted pyrolysis for production of valuable products, and what are our achievables and the catalytic microwave pyrolysis mechanism involved in the production of the valuable products. And finally, the products that we get include the oil, gas, and solid residue. And then we conducted the analysis of these products to find out the industrial applications, and finally the concluding remarks. Okay, the waste plastic are counted as non-biodegradable degradable materials, and the reason for multiple environmental and health issues. These materials are not only harmful for human but also for aquatic and wildlife that mistakenly eat these materials. So plastics are widely used materials in all over the world due to their high strength weight ratio and low cost. However, the economic development of the world is also being affected by the plastic waste. And the management of waste materials is a growing challenge with adversely impacting the environment. So roughly more than 6 billion of plastic waste is produced worldwide, and out of this bulk amount of the waste, only 9% is recycled and 60% is dumped or landfilled, and the rest is burned. And it is estimated that in 2025, these figures can double, means from 6 billion tons to it can reach up to the 12 billion tons. So this shows the intensity of the problem we are going to face in near future. Since it is difficult to process such a huge stock of plastic, a large portion of waste plastic from developing and underdeveloping country is burned due to lack of resources and planning and rapidly shrinking landfill capacity. The burning of plastic along with the fossil fuels is putting on risk the human health, marine life, and the environment. So here, Pakistan is producing 3.3 million tons of plastic waste every year, and most of it ends in landfills, unmanaged dumping, and also it flow into the lands and the water bodies across the countries. So it is causing the major concerns like the environmental pollution, including water and air pollution, and deteriorating the potable water quality, and also creating the health issues and putting the wildlife on danger. So if we pile up this 3.3 million tons that of plastic waste that Pakistan produce in a single year, we can reach to the height of 16,500 meters, and which is the twice the height of the second highest mountain in the world, I mean the K2. So this data is actually extracted from United Nations Development Program conducted in March 2020 in the Pakistan. So you can imagine the intensity of the issue we are going to face in future. Means if we produce plastic in 1 year and we pile up it, it can double the height of the K2, which is the highest peak of Pakistan. So here are the major contributor, the packaging, in industrial packaging and household item packaging, also the food products packaging. It contributes 64% plastic waste, and then it followed by the automobile industry, which contributes about 14%, and other are also the major sources, for example, agriculture and construction industry, electronics, etc. So the major types of the plastic waste are the polypropylene, polyethylene, high density polyethylene, low density polyethylene, polystyrene, polyvinyl chloride, and PET. These are the major type of plastic waste, and among them, the high density and low density are the most important plastics because they produce lot more amount of the plastic waste as compared to the others. So, what are actually the problem? In Pakistan, we waste the plastic bags after a single time use. For that, the government is putting some ban in some cities to replace the plastic bags with the degradable bags. But the remaining waste is being dumped, including refuse plastic, and some of the plastic is being recycled, which has economical value, and it is recycled through mechanical methods. And this recycled plastic comes from the garbage pickers who did not have any data to analyze and also to make a record for future measurements. What are the patterns and trends currently in our country? Because plastic is a cheap, easy to buy, it is a durable and freely available. So it is replacing the steel and the iron. So the people are focusing more on this aspect as compared to steel and plastic due to high cost. But at the same time, there is no implementation of environmental policies and the regulations, and no formal waste recycling and reduction programs. Therefore, the structure is like that. The local system does not develop policies and programs which can check the growth of the plastic waste and the possible remediation for that. What are the mental approach of a common Pakistani? Means we think success means buying more stuff, and plastic is the cheap to buy. So once we use it, why we should care about it? It's government responsibility to manage the waste. So these are actually our approaches which we need to change. For that, we have a clear political agenda setting and civic engagement means we have to make the programs for the education of the Pakistani and the public to show their responsibility and change their behavior towards the waste management. We have clear targeted missions and we have innovation across the sectors, and then we have experimentation to reduce the new approaches to deal this issue. So we have to be creative and effective plastic economy. We should reduce the leakages of plastics into the natural system and also address the behaviors of the uh, people towards this common issue. For that, we have to develop a supply chain. We have to change our behaviors. We need to adapt new policies. We need to collect proper data and use the novel tools like artificial intelligence to create the data and also how we can find the solution to manage these waste problems. We need to think about the alternative products. We have to consider it an important part of economy, and also when you consider anything as a part of economy, we have to know drawbacks of this aspect as well. And at the end, all this enters into the waste management. And once we talk about the waste management, other than burning and landfilling, people normally talking about the plastic, the conversion of plastic into the fuel, and the rest is empty. There are a lot of the gaps which have the question marks. So having this gap in our mind, we have the objective to address the plastic waste management issue through microwave assisted catalytic pyrolysis and the production of the liquid gases, fuel, and valuable carbon residue in the form of carbon nanotubes, which have many multiple novel applications, and creation of the and characterization of the obtained products for possible industrial scale application. So we adopted a micro heating mechanism for the pyrolysis or conversion of plastic waste into valuable products like liquid combustible gases and the carbon nanotubes. For that, the waste plastic is since waste plastic is a renewable source because synthetic plastics are hydrogen-rich feedstock. The hydrogen content of plastic varies from 8 to 14%. However, due to low cost of the virgin plastic, recycling or different forms of plastic is not economically appealing. So alternatively, waste plastic can be valorized into combustible gases, high value carbon and chemical and monomers. So it is also possible to convert plastic waste into high value carbon and hydrogen through microwave heating, which is quite different from the conventional heating because in this process, a heat sector is used to absorb the energy from the microwaves and convert this energy into the heat which goes to the plastic because plastic is an insulator. It does not directly absorb the heat from the microwaves. So microwave pyrolysis based on the principle of electromagnetic heating. Microwave reactor functions at a frequency of 2450 megahertz with the microwave power range of 3 to 60 kilowatt and having the microwave wavelength lower than the 1 meter. So generally a heat susceptor and catalyst is used to break long chain hydrocarbons of raw materials, especially the plastic waste into short chain molecules through rapid microwave heating in the temperature range of 300 to 600, which is highly efficient method and give us selectivity on the product. So in microwave heating, the heating start from the core of the material and the heating expand towards the surface, unlike the conventional heating where heating start from the surface and penetrate towards the core. Therefore, the microwave heating has merits over the many other methods like the conventional pyrolysis. It is an energetic coupling process between heat susceptor and the plastic waste. It is an internally heating process. It is rapid and volumetric process. It gives us highly selectivity and depends upon the dielectric properties of the heat susceptor to be used for the transfer of energy from microwave to the plastic. On the other hand, the conventional heating is conduction based on conduction or convection process. It is externally heating process. It is slow as compared to the microwaves. It is superficial and non-selective. It is difficult to control this process as compared to the microwave heating process. So here is the mechanism of microwave heating of the plastic waste and production of the valuable products. When microwave interacts with the dielectric material or heat susceptor, it forms dipoles. Dipole polarization occurs in the direction of the electric field, and since the electric field changes polarity over time, so these dipole rotates and also shrink and expand. So there is a friction. This friction produces the heat. This heat interacts with the plastic and break the longer chain plastic molecules into the shorter chain molecules, into hydrogen, into carbon dioxide, carbon monoxide, and liquid fuels, being gasoline quality. Generally, this quality of the fuels are produced through this, and along with it gives us the residue. Generally, the residue is the char, which is also an unwanted material and it is a waste. It also have environmental hazards. So our focus is that the residue should not be a char. It should be a something like the structured carbon. And focus here is the carbon nanotubes. So we choose the polypropylene and high density polyethylene, two materials. We use them in pure form and also mix them together. We use a heat susceptor, activated carbon as a heat susceptor, and we use zeolite as a catalyst. We mix these materials in appropriate proportion and then expose to the microwaves, and we obtain the carbon nanotubes, we obtain the liquid oil, and also we obtain hydrogen, methane, carbon dioxide, and carbon monoxide in this process. So this is the summary of the method and materials we use. As I mentioned, we use zeolite, ZSM5 catalyst type, and activated carbon because it is a best material. It has high dielectric loss factor as compared to the other materials. So it is the best intermediate to transfer the heat from microwave to the plastic. So this is the schematic of the experimental setup. It consists of a microwave source. This microwave source is shielded with a pyrolysis chamber, and it has a ceramic fiber block on which we put the feedstock, and then there is a microwave guide. That waveguide focuses the microwaves onto the feedstock, and this feedstock converts into the liquid and also the liquid and vapors and also the gases. So we use the nitrogen as a carrier gas. This nitrogen carries the vapors and the gas towards the condensers and the cold traps, and then we collect this gas in the sampling bags, and also use a gas sampler to check the composition of the gas we produce in this process. Okay, the important thing before we start this process, we have to know that in what temperature range the plastic can be effectively converted into the valuable products. For that, we conducted thermogravimetric analysis and check the initial temperature and oxidation temperature of the plastics. So we observed that in thermogravimetric analysis, the initial degradation of the material or the weight loss starts about 300 degrees Celsius, and oxidation temperature starts roughly around 500 to 600 degrees Celsius. It means we have to pyrolyze, or means the deconstruction of the plastic should be done between 300 to 600 degrees centigrade for effectively conversion of the plastic into the valuable products and the residue. So here we use the three types of the plastic, means high density polyethylene, PP, and the mixture of PP and HDPE. We use the sodium GSM5 catalyst. We use activated carbon as a heat susceptor. Then we keep the plastic to catalyst ratio as a 110. We use micro power of 1 kilowatt, and the temperature of the process was kept constant at 450 degrees Celsius, and the mass of the feedstock was fixed at 550 grams. Then we check the conversion efficiency at 450 degrees Celsius. 80% HDP converted into the liquid and gases, and the rest was 20%, which is the solid product. Similarly, under the same condition, PP change, 80% show change into the liquid and the gases, and 12% was the residue, which we anticipate that it would be the structured carbon, I mean the carbon nanotubes. And later on, we characterize this material to check that either this is a char amorphous material, amorphous carbon, or a structured carbon in the form of carbon nanotubes. Similarly, the mixture of these two plastics produced 84% gas and the liquid, and 60% was the residue. So these findings suggest that if we want to produce the liquid, our focus is on the liquid and the solid product. We should prefer HDPE material in the microwave pyrolysis, and if our focus is on the production of the gases, we should choose the PP because it gives us 40% of the gas, which is much higher as compared to the others. And the HDP give us the 20% solid residue, which is much higher as compared to the PP, pure PP, and its mixture with HDPE. So then the gases we get during this process, we analyze these gases to check its composition, and we find that this gas consists of 81.3% hydrogen when HDP was used as a feedstock, and 78.4% hydrogen when PP was used as a feedstock. And this figure slightly improved to 80.8% when we use a mixture of HDP and PP. It shows that the hydrogen content was almost similar in all three cases. However, the HDP shows slightly higher content, hydrogen content, as compared to the pure PP and its composition and its mixture with HDPE. Okay. So the oil product was a thick wax form. So we performed FTIR analysis of this liquid product to check what are kind of compounds can be in this product. So FTIR analysis shows that at higher wave numbers, we have aromatic uh, carbon hydrogen stretching bands, which show that the presence of alkanes, and at the lower wave numbers, we got the carbon, oxygen, and carbon hydrogen stretching bending vibration showing the presence of alkenes in the product. And at the wave numbers lower than 1000, we have CH bending vibration and CH out of plane bending vibrations showing the presence of alkene and single ring aromatic compounds in the liquid product. These suggest that there was the gasoline scale compounds in the product, which are the heavy waxes, and it is another issue because heavy waxes cannot be used in any direct combustion process. So we can use it as a raw material in refineries and other industries to as a fuel, but it also causes the pollution. Okay, then we conducted actually the sorry. Then we conducted the GCMS analysis of the liquid product to check what is the carbon chain present in the product, and after that we found that the liquid product contained the gasoline range hydrocarbons ranging from carbon 6 to carbon 12 chain, and some heavy carbons having the carbon chain 13 and higher. So these are the different compounds we find through GCMS analysis in the product. So thereafter, the solid residue, which we assume that it is a carbon nanotubes, we perform the XRD analysis of the residue, and we observe the peaks at 2 theta of 25.8 degree and 26.2 degree and 26.1 degree. And the corresponding plane was 002, which shows that these were the multi-wall carbon nanotubes. Some other peaks in the XRD analysis were also observed, which may be the amorphous carbon due to the amorphous carbon or due to the catalyst or the heat sector itself. Okay, then we perform the stem analysis of the residue to check further that either these are the carbon nanotubes, and if the carbon nanotubes, these are the single walled or multi-walled carbon nanotubes. So the image A was the residue produced with the HDPE, the image B was produced with PP, and the image C was produced the mixture of these two. And we can see that in these images, the C shows that the tube structure is much better as compared to the A and B, and the diameter is also in controlled range. The amorphous or the impurity content of the product is always low, is also low as compared to the first two images. And in first case, we produced high gas and the high liquid and residue. But we also see that HDPE in image A also produced amorphous products, and this is due to the high amount of the residue. It means that the reaction was not fully complete, and some residue in the form of the catalyst, amorphous carbon, or the heat susceptor was there in the structure of carbon nanotubes. In PP case, we see that the solid residue was small, but the impurity was also small as compared to the case one, and the impurity level reduced further, and structure of the carbon nanotubes improved when we mix these two. It shows that when we mix two feedstocks, the hydrogen production remain almost same, but the amount of the carbon nanotube decrease over time, and quality improves with the time. So here are some conclusions of our work. The main products are gasoline range liquid fuel, including and hydrogen and carbon nanotubes. especially the multi-walled carbon nanotubes. And FPIR profile shows that carbon-hydrogen bonding of alkanes, alkenes, and alkyne groups in the liquid product. The highest efficiency of hydrogen gas was 126.9 millimolar per gram, which is reasonable as compared to photocatalysis or other methods. GCMS analysis show the presence of the carbon 6 to carbon 12 and some heavy hydrocarbons with carbon chain 13 and plus. The PP produced highest gas yield while HDP produced highest oil and CNT yield, but the mixture of these two produced the small hydrogen and the liquid, but the solid product was more structured as compared to first two cases. The solid residues was identified as multi-wall carbon nanotubes with outer diameter of 30 nanometer to 93 nanometers. And the stem analysis of CNT illustrated the tubular-like structural morphology of carbon nanotubes, having some impurity particles in the structures, which can be removed by proper tuning of the pyrolysis parameters as well as by selecting suitable catalyst and the heat receptor. So optimization of the process can result in well-structured carbon nanotubes, which have tremendous future in nanotechnology and also in the material science and in medical sciences. So especially in engineering and aeronautical industry. So thank you very much.
Thank you very much, Dr. Yasin, for sharing very innovative carbon nanotube works with us. Room is open for questions. Okay, thank you again, Dr. Yasin. Now we will move to our next session, which is a poster session. The PhD students and MS students are involved in this poster session. From PhD, we have two students, Ms. Hina Imtiaz and Ms. Zainab Bashir. And for MS, we have 5 students, Ms. Sara Ijaz, Ms. Amara Arshad, Ms. Asar Abbasad, Ms. Zebun Nisa, and Ms. Khadia Irfan. So now we will see the poster session.
Optical and dielectric applications. So the abstract to my poster is hardosonite was prepared using non-stoichiometric composition by Forrester method at 1200 degrees centigrade. Structural analysis revealed that hardosonite is a major phase and bilastronide is a minor phase with no other impurity. Morphological analysis revealed that irregular morphology with particle size 323 micrometer. The optical band gap ranges from 4.48 to 5.0 electron volt, suitable for sensors, bolometer, and optical electronic applications. Dielectric constant from 3.4 to 7.7 is really from 2.6 to 10 to minus 8 to 4.5 10 to minus 7. AC conductivity were found at 2.1 to 3.8 Simon per meter, making it suitable for low temperature coal-fired applications. So if we talk about the introduction of hardosonite is a tetragonal structured element. In 1953, Broken Hill Associates smelters at Pure, South Australia described calcium in silicon oxide from slag furnaces. So hardosonite is a rare calcium-rich developed by incorporating zinc into calcium silicon oxide system to enhances chemical stability for applications. So it is a ternary compound, always has liquid tension in the biomedical field because of its better biocompatibility, chemical stability, binding strength, and structure toughness in bone regeneration. So but the aim of my research, as it has a particular intention in a medical field before, but there is no any evidence to calculate its optical and dielectric properties, which I have done in my research. So if we talk about the structure of artesunite, was obtained by calculating lattice parameter. It had a tetragonal structure and P421 space. In this structure, a heterocyclic 5-member tetrahedral ring is formed by linked silicon tetrahedral. The rings connected to create a conjoined sheet parallel to C001 and calcium oxide bond hold to the adjacent sheet together. So the methodology of my research for synthesizing artesunite, I use solid state method used for synthesizing the samples, where I have taken 4 samples with different ratios, calcium, zinc, and silicon oxide, and then pulverized in the mortar and pestle, and then make the pellets under a hydraulic pressure of 7 tons. And then I sintered the pellets at 1200 degrees centigrade for 3 hours at the rate of 25 degrees per minute. So this is the mathematical ratios of chemical composition of synthesized samples, and this is the diagram shows the process of methodology. So now if we talk about result and discussion, the phase analysis of these systems tells us that there has 2 phases existed in the system. First is hardosonite, and second is the wollastonite with no other impurity P. So this is the values calculated from the XRD pattern. The trend of the crystal size of the system from top to down, it decreased from the top to down because the concentration of zinc oxide increasing from top to down. We know that zinc oxide is a crystallized resistive material, so that's why we have this trend, and we can clearly see that the Sher formula and WH method have shown the comparative results. So the next technique is the FTIR spectra. FTIR spectra was given in the 2 forms, before sintering and after sintering for the samples. So if we talk about before sintering, there are no show any bands developed in the system, but after sintering at 712, we have we can be attributed to silicon oxide and zinc oxide stretching, which are associated with the formation of hardosonite, which confirm the phase of hardosonite in the sample. The next technique is scanning tone microscopy, which shows that different concentration to the irregular morphology. The average particle size of all the sample was about 323 micrometer, and as we see from first sample to 4th sample, there is a morphology. The whole pattern become less because of the crystallization procedures produced. So the next property is optical properties. We made calculation for 4 values, which is absorption spectra, band gap, Arbach energy, and extinction coefficient. So from the first graph, we can see that there is a phase shift of 4 samples. So we have the absorption peak for the system at 213. Just because the zinc oxide has a good UV absorber. So from the calculations for optical material, we can clearly see that we use this material in antennas and other optical electronic applications. So the next technique is dielectric analysis. Dielectric analysis, we have calculated 3 types of calculation for the dielectric properties, tangent loss, AC conductivity of the system. So by the dielectric properties and the dielectric loss, we have comparative results. As you can see that dielectric constant and tangent loss are inverse to each other, which shows that the sample 3 has a maximum dielectric graph and AC conductivity and minimum dielectric loss. So we can say that we use this material in the bolometers and capacitors and for LPCC application. The conclusion of my poster is the 4 samples internally were prepared by Ferguson method, and by all the results we can conclude that sample 1 has maximum AC conductivity and lowest band gap. These properties make it suitable for the capacitor and LPCC application. And this research has been published in July in Optical Materials, which is a W category journal with 3.92 impact factor. So that's all. Thank you.
Assalamu alaikum. I am Zainab Bashir, a PhD scholar from Lahore College for Women University. I am here to present my poster titled Sol-Gel Synthesized Boron Nitride Thin Films for Antibacterial and Magnetic Applications. Novel devices demand new coatings to assure best dimensional accuracy and maximum efficiency. In this research work, boron nitride thin films are deposited by sol-gel dip coating using two different precursors, boric acid and boron nitrate. Boron nitride is one of the most appealing material from experimental and elemental point of view. It belongs to third nitride family, and at a recent time, its nanostructure has attracted a lot of attention due to its unique properties. The sol-gel dip coating technique was used for the preparation of boron nitride thin films. Boric acid and boron nitrate was used as a starting precursor for the synthesis of boron nitride thin film with different molarity. Ammonia was used as a stabilizer. The SEM micrograph of boron nitride thin film deposited on the glass substrate shows that the film substrate is uniform and continuous. The thin film surface is well covered with the distributed spherical grains of varying sizes and diameter around 100 nanometer. XRG pattern shows that the films are polycrystalline and have preferred orientation along 002 plane with direct relationship of the crystallite size with molarity of the precursor. An increase in thickness of thin film is observed for increase in molarity of boric acid, but thickness was decreased with molarity of boron nitrate. UV visible spectroscopy shows that the band gap increased for both precursor with increase in molarity. The films are found to be ferromagnetic with decrease in saturation magnetization for boric acid, and in case of boron nitrate with increase in molarity of both precursors. The electric constant and AC conductivity also decreases with increase in molarity of both precursor. Boron nitride has remarkable antibacterial activity against bacterial strains. Hence, a boron nitride nanostructure can be used to develop biomedical devices protected against bacterial strains and minimize infections. Thank you.
Assalamu alaikum. My name is Zara Ijaz and my roll number is 56. I am an MA student and my research I have done my research under the supervision of Dr. Tarala Shan, Department of Physics, Lahore College for Women University. My topic is to investigate the structural, optical and dielectric properties of vanadium doped cobalt ferrites by ceramic route method. Introduction. Magnetic materials can be soft and hard. Ferrites are hard, brittle, iron-containing mineral that is usually gray or black and polycrystalline in nature. The substances which are spinel ferrites having the general formula Ap2O4. Here A and B are the metallic positive ions located at tetrahedral octahedral positions, and one key element in their structure is iron. Next experimental setup, we take three powders, vanadium oxide, cobalt oxide, and iron oxide in a stoichiometric ratio. After this, we do the grinding of the materials. After the grinding, we obtain a homogeneous mixture and do a calcination of that mixture at 1100 degrees Celsius for 4 hours. After the calcination, we do the regrinding of the materials, and then we do the characterization of the materials. Results and discussions. First of all, we do the XRD refraction. The characteristic peak of single phase cubic cobalt ferrite structure with the space to 53 verified by the XRD micrograph shown in this graph. The crystallite size and the lattice parameter decreases due to the smaller ionic radii of vanadium than the cobalt. This shows the variation between the crystallite size and the cobalt lattice perimeter and crystallite size. The extra density of produced price also increases because the molecular mass of the vanadium is greater than that of cobalt. The hopping line and bold lines also shows the decreasing trend as which is similar to the crystallite size and the lattice parameter because of the ionic radius of vanadium is less than that of the cobalt. These tables shows us the WH. These are the parameters which are calculated by the WH method, which shows the strain and crystallite size in the produced in the crystal structure, and these are different parameters shows by calculated by the XRD parameters. FTIR spectroscopy. The higher band V1 obtained at 700 degrees Celsius, 700 per centimeter, and the lower band V2 is located at 500 600 per centimeter. Different bonds are formed, which are shown by the graph at 1100 degrees. At 1100 per centimeter, the OH bond is stretching is formed. It is due to the water molecules which are present in water molecules of the KBr, which is present in the FAS ready to prepare the pellets. The second bond is carbon-carbon bond, which is formed with the carbon dioxide produced in the sintering process, and the bonds at 2000 and 3000 is with the CS stretching and the OH bond. Next is visible spectroscopy. This spectroscopy is used to calculate the band gap, which shows the increasing trend because of the crystallite size that decreases. This graph shows the Mohs relation and Van Dams relation of the refractive index and the band gap energy. Dielectric spectroscopy. This graph is for the dielectric constant and this is for the tangent loss. Both shows the same trend at lower frequency. These are both are high, and the high frequency both are low because at the high frequency the grains are conducting and the grain boundaries, and the grains are non-conducting and the grain boundaries are conducting. This is the graph of the AC conductivity, which shows at the low frequency the conductivity is less because the grains are not conducting, and at the high frequency the grains are conducting. So this shows the increasing trend. This is a graph of the pole-pole plot, which shows that the grain boundaries play a dominating role over the conduction phenomena, and this is graph is for the Bode plot, which shows the frequency response of the graph. We have calculated the dielectric properties because our material are moving towards the insulator as confer for the from the increasing band gap. Conclusion. XRD and FAR have verified the existence of single-phase cubic field ferrites. The presence of induced lattice strain in the ferrites by WH method shows us the different type of the crystallite size, and the FAR study shows a remarkable vibrational bands. The optical energy band gap shows by increasing the vanadium content, which is studied by the UV visible analysis. The pole-pole plot displays one semicircle for all the samples, indicating that only grain boundaries are responsible for the convection behavior, which suggests that the grain boundaries volume has a dominating role over all the convection. So this is these are some references. Thank you.
Assalamu alaikum. I am Amara Arshad. So today I will represent the poster of my topic is that the first principal and experimental study of aluminium substituted zirconium oxide for photovoltaic applications under the supervision of Dr. Talat Zishan and Dr. Murtaza Salim. Introduction. First principal and experimental study of aluminium substituted pure zirconium oxide thin films for photovoltaic applications. We use AB initio calculations. The electronic and optical properties of this material. We use aluminium concentrations. Thin films were prepared through sol-gel spin coating method. Prominent difference was observed between the results of electronic and optical properties of zirconium oxide thin films. Methods. We use two methods, computational method and experimental method. In computational method, the electronic and optical properties of pure zirconium oxide and aluminium doped zirconium oxide thin films density functional theory was implemented in vein 2K. In experimental method, we make a solution zirconium nitrate and then add the citric acid. We make a thick sol gel. Then zirconium nitrate and aluminium concentration we use in citric acid, and then stirred at 700 rpm at 100 degrees centigrade for 10 minutes. Then we use the spin coating method. We obtained the thin films drying at 100 degrees centigrade for 10 minutes and thermal treatment at 600 degrees centigrade for 2 hours in furnace. Results. First of all, we will discuss the electronic properties. In electronic properties, in figure 1, we use total density functional states for pure and aluminium doped zirconium oxide thin films. In these graphs, the loss of tensity states between the Fermi level and conduction band is indicated by the semiconductor character of zirconium oxide. For all concentrations of aluminium doped zirconium oxide, the p state of oxygen atoms move across the Fermi level towards the conduction band. In figure 2, EDX spectra of aluminium doped and pure zirconium oxide, it is seen that the spectra as the highest peak is witnessed of aluminium doped zirconium oxide thin films, and peak position for pure zirconium is at 2.05 kilo electron volt.
My name is Asarim Basat. My topic is chemical and optical properties of zinc oxide doped silica membrane for the purification of water. I have done this thesis under the supervision of Dr. Nikasna. Now come up to the abstract of this research work. Silica membrane was employed by soldier techniques. Triethyl orthosilicate was used as a silica source. Triethyl octosilane was used as a surfactant material. Polyvinyl pyroiodine and butanol was used as a precursor materials. And sodium citrate was used as a reducing agent. To maintain the pH of the solution, we use an ammonia solution. Chemical functional group was identified by FTR. Surface morphology was characterized by scanning electrons microscopy. Optical properties of silica membranes was characterized by UV visible spectroscopy. Mutability of the membrane was studied by measuring the contact angles. The main challenge to achieve ST6, which is clean water and sanitation, was successfully achieved with an interval for rejection ability 93 to 98%. Zinc oxide doped silica membranes were effective antibacterial agents against pathogenic microorganisms. Now come up to the introductions of this research work. First is silica membranes. As you know, silica has very low thermal conductivity and gives us very good absorption capacity. When zinc oxide doped with silica membranes, they give us 3D gel-like a network, which is good. Now the membranes used for the filtration process because it gives us a super hydrophilicity membranes. Now next is experimental work. We add PVP, PVA and PEG into the solution of butanol and distilled water. After 15 minutes of agitation, we use a silica source and surfactant materials into the solutions. Again 30 minutes of stirring. Sodium citrate are added into the solution and injected NH4 into the solution. After 13 minutes of agitation, silica salts are prepared. We use different concentration 5, 10, 15 and 20 of zinc oxide of silica membranes into the solution. Now dry the salt into the incubator at 50 degrees Celsius. Now peel off the membranes because the membranes are prepared with the help of a tweezer. Membranes gives us two applications. First is antibacterial activity and second is nanofiltration. Now come up to the results and discussion. First characterization technique is ultraviolet visible spectroscopy. Invisible ultraviolet.
Assalamualaikum. My name is Evanisa. I am going to represent my poster presentation that is on title Synthesis and Characterization of Zinc Oxide Nanostructures. The aim of my work is to evaluate synthesized zinc oxide nanoparticles using Ugrilla spiva seeds extract. 5 samples were prepared by increasing the concentration of zinc sulfate. While the green synthesis method is used for the synthesis of zinc oxide nanoparticles. Firstly, preparation of seed extract was done. As you can see in this flow chart, the preparation of the seed extract was done, while as the synthesis of zinc oxide nanoparticles are done. As you can see in this flow chart, firstly, seed extract was added in the zinc sulfate solution, and this solution was shown in this figure. This solution was added in zinc sodium hydroxide solution, and the resultant solution was shown in this figure. Then this mixture was undergoes different process: centrifusion, washing, filtration, drying, and grinding. Then the obtained zinc oxide.
Assalamu alaikum. My name is Hadia Irfan, and my title of poster is Electronic and Optical Properties of Magnesium Doped Zirconium Oxide for Optoelectronic Applications. First, I'll start with my introduction about thin films. Thin film technology plays an important role in the advancement of optoelectronic devices, and they are used to study and measure the physical and mechanical properties of materials in various fields. And the method of smearing thin layers onto a substrate are acknowledged as thin film deposition techniques. Deposition techniques plays an important role in the formation of thin films. And next is my methodology of my research. There were two methods used. First was experimental. In my experimental method, the thin films were for pure and magnesium doped zirconium oxide with concentrations of 3.7, 5.5, 12.5, 5.5 and 12.5% was used. And first the gels was prepared.
Okay, with this poster session, now we are with our last speaker, Professor Dr. Michael Hunt. He's working as Associate Professor in the Department of Physics, Durham University, UK. He has published almost 100 papers with citations around 1453. He is highly cited researcher among all the institutes. His expertise are characterization of growth, modification, structure, electronic devices, energy generator and storage, graphene, transition metal chalcogenides. He is involved in number of book chapters and projects. So please, Dr. Michael Hunt, share your work with us.
Thank you so much, and thank you so much for inviting me. I'll just share my my screen.
Yes, please.
That will work. Can you see the first slide?
Yes, we can see your first slide.
Excellent. Thank you very much. So in this particular presentation, I'm just going to talk to you about a small aspect of our work, which is the use of few-layer graphene in supercapacitor applications, particularly as an electrode, an additive or an interfacial layer in aqueous supercapacitors. So very briefly, I would like to just indicate why we would be interested in supercapacitors as an energy storage technology. And as I'm sure people in your country are very particularly aware, there is an extremely pressing need to mitigate the effects of climate change, and in particular to develop renewable energy in order to reduce carbon dioxide emissions. Now, one of the problems associated with renewables is their intermittent nature, which creates an imbalance between supply and demand. For example, solar power is only generated during the day, and often, at least in cooler countries, one needs heating and lighting in the evening when that power is not being generated. And there are a whole range of energy storage solutions that exist, and I've just shown some here, which are large scale but vary in efficiency. But electrochemical energy storage, in particular batteries and capacitors, are the most ideal for domestic and portable use. So we should just discuss a little bit more about the differences between a supercapacitor and a battery. So the storage mechanism for energy in a battery is Faradaic chemical reactions that involve the bulk of the electrode materials, whereas an electrochemical double layer capacitor involves physical absorption of ions at the electrode surface, as I'll show in a bit more detail in a moment. The result is that there is somewhat different performance between the two. Electrochemical supercapacitors have very high specific powers, which means that they can supply energy extremely rapidly and be recharged extremely rapidly. However, compared to batteries, they have much lower specific energy storage. We've got this illustrated over here on the left-hand side of the slide with Aragone plots, which plot specific energy, specific power against specific energy, with the diagonal lines being the typical discharge time for the electrochemical storage device. And the key thing that one wants to achieve in any electrochemical energy storage device is to push towards the upper right-hand quadrant of this Ragone plot to increase both the specific energy and the specific power of the energy storage device. And why we would want to focus on supercapacitors is that not only do they have a very high power density, which makes them particularly useful for certain applications where rapid power delivery is required, such as the acceleration of an automobile or regenerative braking within such an electric car, they have also the capability of being cycled. They have the possibility of being cycled over a very, very large number of cycles. So if we look, for example, at the typical number of cycle times that a battery could have, the cycle life of a battery is about 1,000 times. We've probably all come across the situation where we've had to replace the battery in a mobile phone or replace the phone simply because the battery no longer holds charge, whereas a supercapacitor can have upwards of 500,000 cycles without degradation. The other great advantage of a supercapacitor over a battery is that batteries at the moment are primarily based on lithium-ion technology. The mining of the materials required for that, the lithium, the cobalt, etc., is extremely environmentally unfriendly. And moreover, there is no way in which lithium-ion batteries can be recycled in the bulk. Whereas with supercapacitors, we can use recyclable materials, earth-abundant materials, and not only address the problem of energy storage, but also address the problem of the environmental sustainability of that particular storage technology. And although I won't talk about it today, one of the projects that we have undertaken is to use biomass waste in order to produce the materials that we have included in supercapacitors. So just briefly, I'll outline how a supercapacitor works. So we're all probably familiar with the idea of a double-layer, a two-layer capacitor. We've seen the picture, no doubt, in our undergraduate studies of two plates with a distance d between them, that one has a positive charge and one has a negative charge. And we can simply express that in terms of the equation for a parallel plate capacitor given over here on the left-hand side of the slide. In an electrochemical double-layer capacitor, what we have are two charged electrodes that are placed in an electrolyte which contains ions. And in the simplest model, one can imagine that as we charge each electrode, ions of the opposite charge approach, and they form at each electrode surface a capacitor. So we have basically two capacitors in series, one associated with a positively charged electrode with negatively charged ions assembling close to the surface, and vice versa at the negatively charged electrode. The result of that, the distance d that we have, is very much smaller than we typically meet in a standard parallel plate capacitor. And as a result, the capacitance is extremely enhanced. Likewise, there is a linear proportionality between the capacitance and the area of the electrode. So we use highly porous materials. We want to maximize the surface area in order to make A as large as possible. By making A and D as large as possible, we can produce supercapacitors with specific capacitances as high as 100 farads per gram or more. One of the things that we're going to use in our supercapacitors is graphene. And that was the focus of some of our research. And in particular, we focused on the use of graphene due to its high surface area. Its specific surface area for a single layer of freestanding graphene is 2,630 square meters per gram, which is absolutely massive. It also has outstanding electronic properties. For example, mobility in freestanding graphene is absolutely huge, and excellent mechanical properties, all of which would be highly desirable for incorporation into an energy storage device. I just want to make a little note about nomenclature here, because it often gets mixed up in the literature. Graphene strictly is a single layer of carbon atoms, with each atom bound to three neighbors, as shown here in the center of the slide. What we're going to be dealing with today are few-layer graphenes. That's 3 to 10 well-defined stacked graphene layers. Anything bigger than 10 is micrographite. And it's important also to differentiate between graphene and reduced graphene oxide. A lot of what's called graphene in the literature turns out to be RGO, and that has a high defect and oxygen group density, which will affect, of course, the behavior of the material. So a whole range of different supercapacitor structures that have been made using graphenes, and they've particularly involved the use of reduced graphene oxide, which is rather crumpled and disordered, as you can see here, often called chemically modified graphene, and sometimes also doped with, for example, nitrogen-containing groups to increase their conductivity. The behavior of these few layer graphenes, these reduced graphene oxides, these chemically modified graphenes, is generally pretty good. However, what we particularly wanted to explore were not functionalized graphenes, but graphenes that were unfunctionalized. And the reason for that is that the functionalization and production process for reduced graphene oxide is highly environmentally unfriendly. So there are a number of different ways that we can produce graphene oxide. And this radar diagram over here, the set of radar diagrams, illustrates them in terms of their yield, purity, their cost, its scalability, etc. So the most commonly used form of graphene in supercapacitors, reduced graphene oxide, has a high yield and high scalability, but it's actually extremely environmentally unfriendly because one has to use the Hummers method. So basically, extreme acidic conditions in order to oxidize the graphene. And then one can use perhaps slightly more environmentally friendly approaches to reduce the graphene oxide to RGO. But it's something that I think in terms of environmental sustainability is poor. The best quality graphene that you can have is produced by micromechanical exfoliation, which is the tape peeling technique. The problem with the tape peeling technique, of course, is it isn't very scalable. We use liquid phase exfoliation, which is highly scalable and was pioneered by Patton's group back in 2014. Actually, Jonathan Coleman's group. Patton was the first author. And it involves placing graphite precursors into a liquid phase and then basically applying a high shear force using a high shear mixture to basically tear the graphite platelets apart and form few layer graphene. Our particular spin on this is not to use a surface energy matched organic as the liquid phase, but to use a stabilized aqueous suspension. So we use water and we use a surfactant, Triton X100, to ensure that the process is green and recyclable. And why would we want to make our own materials? Well, there was a nice study by Cowling and co-workers back in 2018. They looked at about 60 different samples of graphene provided by commercial suppliers. And in some cases, you can see that had considerably less than 100% carbon content, and even the best of them only had 50 to 60% of sp2 carbon content, which means that a large fraction of the material could not be described as graphene. So our aim is to make binder-free few-layer graphene electrodes, and that aim is to then determine the optimal active few-layer graphene conductive additive to find out what few-layer graphene behaves the best and is the most active in an electrochemical double-layer supercapacitor, and then include it as a conductive additive into a standard electrode. So we characterize our graphene as follows. We basically start with our graphite flakes. We shear exfoliate them to form few-layer graphene, and here's a complete film of few-layer graphene shown towards the center of the slide. And we used Raman-based metrics to determine the thickness and linear dimension. So if you look at the Raman spectrum of the few-layer of the graphite flakes and that of the few-layer graphene, you can see that they change quite considerably. There are three main peaks labeled D for defect, G for graphite, and 2D. And you can see that the shape changes and the relative intensity changes. And from that shape and intensity change, we can determine, using metrics that are available in the literature, the thickness and the linear extent. So we find that our graphene platelets are 4 layers of graphene thick on average, plus or minus a layer. And that's fairly independent of the way in which we produce them. However, if we increase the shear speed during shear exfoliation, we make the platelets smaller. They vary in linear dimension from just above a micron to about 0.75 micrometers. We also check the linear dimensions by using scanning electron microscopy. And here are a bunch of graphene platelets that have been filtered onto an anodic aluminum membrane, and we simply count them, and we count their areas. And finally, we can determine the nature of the defects within the graphene as well by looking at the Raman spectra, fitting them carefully and taking the ratio of this peak here, known as D primed, to the D peak. And we find from this ratio that we predominantly have vacancy defects within the graphene few-layer graphene that we produce by shear exfoliation. So we take the shear exfoliated material, we vacuum filter it to produce freestanding binder-free electrodes that we that we combine with a membrane, either CellGuard 2500 or a glass fiber membrane. And we use a potassium hydroxide electrolyte and assemble 2 electrode electrochemicals test cells. And we characterize them by looking at the cyclic voltammetry and the galvanostatic charging and discharging. Now, we're probably very aware with the simple capacitor equation that the charge is capacitance times voltage. So if we differentiate that, we get current is capacitance times the rate of change of voltage. So in a CV experiment, we keep the rate of change of voltage constant and we monitor the current. So we should get a flat line here, and then we change the direction of the current. We should get a perfect rectangle. Because of the finite resistances in the cell, we get a slightly curved and distorted rectangle. And for galvanostatic charging and discharging, we apply a fixed current and we look at the change in potential with respect to time. The slope of the galvanostatic charging and discharging curves gives us the capacitance. And also you can see that there's a little step as we change the direction of the current from charging to discharging, and that enables us to determine the effective series resistance in the supercapacitor cells. So we first produced a series of few layer graphene samples. So electrodes consisting of graphene alone. And as you can see from the cyclic voltammetry, they are very rectangular indeed, which indicates extremely good electric double layer capacitor behavior. Likewise, the charging and discharging curves are extremely linear. And we find with cycle number, not that the specific capacitance decreases, it in fact increases. So the more we cycle these materials, the better they get, not the worse. So that's the good news. The bad news is if we actually look at the values of the specific capacitances, they're not particularly high. And we kind of expected this. We were looking to find the best materials we can use as a conductive additive with another material because we'd expect the few layer graphene platelets to restack. And you can see this in these scanning electron micrographs, that there is clear evidence of restacking of the layers. And this restacking reduces the surface areas. The surface areas of these particular few layer graphene electrodes is of the order of about 10 to 15 meters squared per gram. Compare that with the theoretical value of 2,630 meters squared per gram of a freestanding single layer of graphene, and you can see why that these perform less well than would be expected theoretically. And the stacking also means that compared with the very crumpled and disordered reduced graphene or chemically modified graphenes, the stacking is very good. In those other samples, the stacking is poor, which increases their porosity. But you can see over in the right here, there's something very interesting. The specific capacitance increases as the linear dimensions of the graphene platelets, of the few layer graphene platelets decreases. And we can understand that by appealing to some work by Velitsky et al. From a couple of years ago, who looked at the capacitance micro areas on the basal plane and on the edges of graphite, and they found that a perfect edge plane on graphite had a much higher specific capacitance than the basal plane. So obviously to have an active additive that both helps the conduction of an electrode made of another material and actually contributes towards the specific capacitance, we want to use small platelets. So we created our composite electrodes consisting of activated carbon and few layer graphene by starting off with an activated carbon electrode produced by mixing the carbon with a binder. Usually at this stage, we would add a conductive additive such as carbon black in order to reduce the resistance of the electrode material and improve its performance. In this case, as we can see over on the right, we take a graphene suspension and we filter it through the electrode material to create a graphene-infused electrode, which consists of graphene within the main body of the electrode and a complete layer of few layer graphene assembled at the electrode surface. And it's this electrode surface that we use as the current collector. If we undertake measurements of the electrochemical performance of these particular graphene-infused supercapacitor electrodes using graphene with a relatively narrow-sized platelet size distribution, we find that compared to with an undoped activated carbon electrode, that is a carbon electrode with no conductive additive, there is a a small increase in the specific capacitance, but a very large reduction in the series resistance. And reducing the series resistance will increase the power output of the supercapacitor, thereby increasing its performance. So what we did quite naturally was increase the amount of few layer graphene that we infused into the activated carbon electrodes, and we found that actually there was a fairly steep drop after an initial small quantity was added, and the resistance of the supercapacitor electrode increased. So one thing we thought was perhaps that we were having a size distribution that was too large, and that we could improve performance by having smaller graphene platelets that would infuse better within the electrode, make better links between the activated carbon particles, and assemble less at the surface. In fact, the opposite was true. So we've got here a narrower distribution, so of smaller platelet sizes that we've infused in the same way, and you can see that the cyclic voltammograms are considerably less rectangular, and there's more curvature to the galvanostatic charging and discharging curves. And if we look at the sort of the amber-coloured squares that are on the plots for specific capacitance and for effective series resistance, you can see that generally there is a worse performance. So we went in the other direction. We chose a very broad distribution of platelet sizes. And we can see that, if anything, there is a further improvement to the shape of cyclic voltammograms and to galvanostatic charging and discharging. And you can see from the blue dots here that for every single concentration, we have improved performance. And particularly up here for relatively low concentrations, this is 7% of graphene to activated carbon, that we have a considerably enhanced performance compared with other compositions. And this is also associated with a very good series resistance for all of the compositions of this broad distribution that we tried. And finally, we compared with just adding a standard conductive additive, which is tin cal C65, which is shown on the SEM image over here, with the activated carbon shown on the image below. And this is our kind of standard electrode configuration. And these are given by the black squares. And you can see that, again, at all compositions, there is an increase in performance associated with the broad distribution of graphene platelets. So we can therefore investigate this a bit further by looking in detail at comparing this broad distribution of few layer graphene to the activated carbon on a Ragone plot, where we plot the energy density in watt-hours per kilo against the power in watts per kilogram. And you can see over a variety of discharge conditions, so these are a series of discharge currents ranging from 0.1 to 1 amp per gram, you can see that that if we infuse activated carbon with a broad distribution of platelet sizes of few layer graphene, we get an enhanced performance compared with a standard carbon black. We believe that this is because, as we say, we infuse the graphene into the body of the electrode, and you can see where these arrows point there, where we've taken a cross section through one of the electrodes, that there are graphene platelets, and these provide links between the activated carbon particles and therefore improve the conductivity of the electrode. But unlike carbon black, which does the same thing, the graphene platelets are electrochemically active. They also participate in creating the capacitance of the electrodes. So as a result, when you add a normal conductive additive, a carbon black, you tend to reduce the surface area slightly and reduce the specific capacitance of the material, or at least not enhance it significantly. Here, when we add few layer graphene as a conductive additive, we enhance the behavior of the electrode, both in terms of its conductivity, but also in terms of its capacitance. And the reason why large platelets generally work as a broad size distribution is that we prevent too much accumulation of few layer graphene in the electrode material. So we prevent it from starting to go from a situation where we have a beneficial concentration to blocking the pathways by which the ions can reach the surface of the activated carbon particles, and it forms a continuous backplane which reduces the contact resistance with any current collector that we use. So to draw conclusions, shear exfoliated few layer graphene alone is actually quite poor as an aqueous supercapacitor electrode, and that's due to strong restacking unless you chemically modify the fuel air graphene. The edges of fuel air graphene actually are quite electrochemically active. So ideally, if you want to use it either in any kind of supercapacitor application, you should use platelets that are relatively small in linear dimension. We've shown that we can use shear exfoliated fuel air graphene as conductive additive, but we found, rather contrary to what we originally expected, that fuel air graphene material with the broadest size distribution works best and outperforms a reference material which is constructed using a standard carbon black as an additive. And we think this is due to the infiltration of the fuel air graphene into the electrode bulk, and in particular that this is somehow self-limiting, and the formation of a conductive backplane. And I thank you for your attention. So if there are any questions, please ask.
If there is no questions, thank you very much, Dr. Michael Hunt, for just this nice talk.
Thank you.
And with this talk, this webinar, Material Science in Current Era, has come to an end. I'm pleased to speak to you at the conclusion of this 4th international webinar of the Physics Department, organized by Al-Biruni Physics Society. I understand that it has been a productive meeting and that good progress has been made. I am thankful to everyone for taking part and contributing to this success. I am grateful to all of you for being part of this effort to strengthen material science community. This webinar is an excellent example of such cooperation. I'm really very thankful to our Vice Chancellor, Professor Dr. Bushra Mirza, for providing the vision to conduct such collaborative activities, and of course, the speakers for gracing the webinar and organizing team without which such type of international events are not possible. I'm also thankful to Mass Communication Department of Lahore College for University Lahore and media team of Web TV LCWU, especially the manager communication Mr. Naveed Iqbal and technical engineer Mr. Ahmed Kazim for helping to conduct the webinar live, and the Director IT, Mr. Saptain, for the smooth running of internet. They were ready to solve any problem at short notice. In short, the contribution of concerned has made this important event to a successful conclusion. I now declare this webinar closed and hope to see you all in the February 2023 at 2nd International Conference, Emerging Trends of Physics, organized by the Physics Department, Lahore College, Pavova University, Lahore. Thanks a lot for taking time out of a busy schedule, and see you again. Take care and goodbye.
Recording stopped.